A star is dying right now, as you watch this video. Betelgeuse, a red supergiant in Orion's shoulder, is slowly collapsing under the unbearable pressure of its own gravity. The core is collapsing, the temperature inside is reaching billions of degrees, iron is fusing into nickel, but nickel can no longer burn. The thermonuclear reaction stops, the pressure disappears, and gravity begins its final victory. When this happens, not if, but when, the star will explode with a force that the human mind cannot fully comprehend. The supernova will light up the sky with a flash brighter than a billion suns, and this event will forever change our understanding of the cosmos. For years, astronomers have reassured us that humanity has time, tens of thousands of years, maybe even hundreds of thousands of years before the explosion. Betelgeuse is indeed old, but not old enough for an immediate catastrophe. The explosion should happen somewhere in the distant future, so distant that our distant descendants will see it, not us. They were wrong, and in the summer of 2025, it became clear just how wrong. A group of astrophysicists from the Harvard-Smithsonian Center completed a review of models of the star's evolution using new data and accurate measurements from high-resolution spectroscopy. They analyzed the star's pulsations and internal structure, and the results were shocking to the entire scientific community. Betelgeuse's core is contracting much faster than outdated models from previous decades predicted. Thermonuclear processes inside have unexpectedly accelerated. The iron core is growing faster than expected, and collapse now seems not just inevitable, but frighteningly close. An anonymous source from the research team shared information with journalists that changed everything. We have 3 years, maybe 5 years, maybe even less time before the explosion. Betelgeuse will explode within our lifetime, and we will witness something that no human has ever seen in the written history of civilization. The supernova explosion will occur close enough to light up the Earth brighter than the full moon for weeks or even months. Night will literally turn into day, the sky will change forever, and we will all be there to see it. If the source is telling the truth, if the calculations are correct, if Betelgeuse is truly in its final throes before its final collapse. Stay tuned until the end, because we will take a detailed look at all the alarming signs of the impending explosion. We will explain what humanity will see when it finally happens, and discuss the real reasons why astronomers prefer to remain silent about the most important discovery of the last decade. And if this cosmic mystery has hooked you as much as it has hooked me, be sure to like this video and subscribe to the channel so you don't miss any important updates as events unfold. Write in the comments where you are watching from, what time it is there, and whether you are ready to see a supernova explosion with your own eyes in the coming years. And if you want to help our community grow and develop, share this video on social media, X, Facebook, Reddit, or just in your group chats with friends. You are the only reason we can continue to explore and tell such incredible stories. Thank you so much for your continued support. Let's start with what's happening to Betelgeuse right now. Betelgeuse is one of the most recognizable and famous stars in the entire night sky. It is incredibly easy to find, even for someone with no experience in astronomy. In winter, just look at the constellation Orion and find the 3 bright stars of the legendary Hunter's Belt. The 2 brightest stars above the belt form the shoulders of this celestial warrior. The left shoulder is marked by a reddish twinkling star, and that is Betelgeuse, Alpha Orionis, the 9th brightest star visible from our planet. But to call it an ordinary star would be a gross mistake, because Betelgeuse is a real cosmic monster. It is a red supergiant of such incredible size that if you somehow moved it to the place of our Sun, its hot surface would easily engulf the orbits of Mercury, Venus, Earth, and Mars, and would continue to expand almost to Jupiter. Betelgeuse's diameter exceeds that of the Sun by 700 times, its mass is 900 times greater, and its luminosity is staggering, 100,000 times more powerful than our star. A true giant among the giants of space, and this giant is slowly dying before our eyes. All stars in the universe die sooner or later. This is the inexorable physics of space. A star exists thanks to the delicate balance of 2 opposing forces fighting within it. Gravity constantly pulls all the mass inward, trying to compress the star into a tiny point. The pressure of thermonuclear reactions in the core pushes the matter outward, resisting this compression with all its might. As long as the hydrogen in the core continues to burn and turn into helium, this balance is maintained for decades. The star remains stable and lives peacefully for millions or even billions of years in a row. But hydrogen cannot burn forever. Its reserves are finite even in such giants. When hydrogen is completely depleted at the very center of the core, the temperature inevitably drops. The pressure decreases critically, and gravity slowly begins to win this ancient struggle. The core collapses under its own weight, but this compression raises the temperature to new extremes. Helium ignites and begins to burn, forming carbon in its reactions. The process continues to escalate. Carbon burns and creates oxygen. Oxygen fuses into silicon. Silicon continues to burn and ultimately creates iron at the very center. It is at iron that this process stops forever and finally. Iron categorically refuses to burn in thermonuclear reactions because its fusion into heavier elements does not release energy outward, but rather consumes it from the surrounding space. The thermonuclear furnace inside the star suddenly goes out completely. The pressure disappears instantly, and gravity gains absolute, unlimited power over matter. What happens next unfolds at incredible speed in a matter of seconds. The core collapses catastrophically fast, shrinking from the size of a small planet to the size of a normal city in literally an instant. The density of matter becomes so incredible that protons and electrons merge together, turning into neutrons. A neutron star is born in the heart of the dying giant, or a black hole is created if the mass is large enough for this to happen. The outer layers of the star begin to fall rapidly inward toward the collapsing core under the force of gravity. Trillions and trillions of tons of hot matter crash into the neutron core at speeds of tens of thousands of kilometers per second. The impact is of monstrous force, the matter rebounds with incredible energy, and the shockwave begins its journey outward. It rushes through all the layers of the dying star, heating the gas to billions of degrees instantly, and an explosion of unimaginable power occurs. The supernova illuminates space with a flash so bright that a single dying star begins to shine brighter than the entire galaxy with its hundreds of billions of stars. For a brief cosmic moment, Betelgeuse will emit more light than all 200 billion stars in the Milky Way combined. The energy released in a few seconds of the explosion will be equal to all the energy that our Sun will emit in 10 billion years of its existence. And we will see this cataclysm with our own eyes from Earth. This is because Betelgeuse is relatively close to us in cosmic terms. Only 600 light-years separate us. This is a huge distance in human terms, but on a galactic scale, we are practically neighbors. Betelgeuse is one of the closest massive stars capable of becoming a supernova in the foreseeable future. And when it finally explodes, the light from that explosion will travel through the cosmic void and reach our planet. Imagine a typical night sky above your city or village. Orion slowly rises above the horizon on its eternal journey across the sky. You stand and look up at the familiar constellations. Suddenly, one of the stars begins to grow brighter before your very eyes. Quickly, rapidly, inexorably. In a few hours, it becomes noticeably brighter than any other star in the entire sky. Brighter than shining Venus, brighter than majestic Jupiter, brighter than anything you have ever seen at night. By the end of the first night after the explosion began, it is already shining like a bright crescent in the sky. After a day, its brightness is comparable to that of the full moon, flooding everything around it with a cold, reddish light. You can see this star even during the day in bright sunlight, just a bright red dot hanging in the blue sky next to the sun. Nights will cease to be truly dark for weeks and months. The shadow of the moon on the Earth will be accompanied by a second, sharper shadow from Betelgeuse. You will be able to read a regular paper book outside late at night without any additional lighting. Cities will begin to save on nighttime street lighting because the sky itself will emit enough light for safety. The world will be transformed beyond recognition. And then, very slowly and gradually, the light will begin to dim day by day. Weeks will turn into months of slow extinction of the cosmic fire. The brightness will steadily decline from its peak to normal. In a year, the supernova will return to the brightness of an ordinary star in the sky. In 2 years, it will disappear from view with the naked eye forever. Betelgeuse will go out completely and irrevocably. Only an expanding cloud of hot gas will remain in its former place, a nebula created by the explosion. And at the very center of this cloud, a neutron star or black hole will rotate, the last cold remnant of what was once a majestic giant. But all this will happen later, months and years after the explosion. The main question that preoccupies scientists and ordinary people alike is, when exactly will this happen? And all signs point to a frightening answer. Soon, very soon. Astronomers first became seriously suspicious at the very end of 2019. Betelgeuse suddenly began to dim noticeably and inexplicably to observers. Usually, its brightness varies slightly in a natural way. Red supergiants constantly pulsate, periodically expanding and contracting, which affects their luminosity. But what began then was radically different from the usual fluctuations. It was a completely different phenomenon. The brightness fell stronger and stronger, frightening observers. By February 2020, the star had lost more than 60% of its usual brightness completely. It became dimmer than Bellatrix, another star in the Orion constellation, which is usually much weaker than Betelgeuse. Astronomers around the world became seriously concerned, and the media instantly picked up on the sensational story. Newspaper headlines and news sites literally screamed, "Betelgeuse is exploding right now, a supernova is inevitable and imminent, the end is coming faster than we thought." But scientists remained cautious and did not rush to conclusions, understanding the complexity of the situation. The dimming of the star could have many other, more prosaic causes unrelated to an explosion. Perhaps giant clouds of cold dust had formed on the surface of the giant, temporarily blocking the light. It was possible that a huge amount of material had been ejected into space, creating an opaque veil between the star and us. Or it could simply be an unusually strong normal pulsation, the amplitude of which happened to be greater than usual. A supernova explosion remained only one of the possibilities, but far from the only likely one. By April 2020, Betelgeuse's brightness had slowly begun to return to normal. By June of that year, the star had completely returned to its usual luminosity, as if nothing had happened. The astronomical community breathed a sigh of relief around the world. The false alarm turned out to be just that. Betelgeuse did not explode. It simply went through an unusual phase of temporary dimming. Or was it not so harmless after all? Later research with careful analysis of the data revealed something disturbing. The dimming was caused by the release of a truly enormous amount of dust into the surrounding space. The star literally ejected a massive cloud of material, hot gas and solid particles, which then condensed in cold space and formed an opaque dust veil. The cloud slowly moved through the space between Betelgeuse and Earth, effectively blocking most of the light. This is a natural process. Red supergiants regularly lose mass in this way. They constantly eject matter into the surrounding space in the form of stellar wind. But here's what really bothered some of the most attentive scientists in this story. Why was the ejection so massive and powerful at that particular moment? Why did the star eject such a huge amount of material at that particular moment? Red supergiants do indeed constantly lose mass through stellar wind, but such large-scale catastrophic ejections are extremely rare. They only occur when the star becomes critically unstable inside, when internal thermonuclear processes begin to behave chaotically and unpredictably, when the delicate balance between gravity and pressure begins to be seriously disrupted, when a star rapidly approaches its inevitable end. The darkening of 2019-2020 was the first serious warning of impending problems. The first clear sign that something fundamental was changing inside the giant. But the vast majority of astronomers did not attach much importance to it at the time. They simply said, "It is an interesting and unusual event, but not critical to the fate of the star. Betelgeuse will live quietly for many thousands of years without any problems, perhaps even hundreds of thousands of years before its final collapse. Humanity definitely has enough time to observe it." Then came the years 2023 and 2024 with new alarming discoveries. An amateur astronomer in Japan, who patiently tracked Betelgeuse's brightness every clear night, noticed a strange and disturbing pattern in the data. The star's pulsations began to change noticeably in an inexplicable way. Betelgeuse usually pulsates with a fairly stable period of about 400 days between peaks. regular and predictable, like a cosmic clock. But from the middle of the year 2023, the period began to steadily shorten for no apparent reason. 400 days became 380, then 350 days between peaks. By the beginning of 2025, the period had fallen to 320 days. The pulsation period of any star is directly related to its internal physical structure. A star expands and contracts like a giant bell vibrating after a powerful blow. The frequency of these vibrations depends entirely on the size of the star, its mass, and its internal density. A change in the pulsation period necessarily means a change in these fundamental parameters inside. Betelgeuse slowly contracted from within under the influence of its own gravity. Not the outer layers of the star, they continued to expand outward, as befits a red supergiant. But deep inside, the core was inexorably contracting day after day. It was becoming denser and hotter with each passing month. Thermonuclear processes inside were accelerating rapidly, and this internal contraction of the core affected the pulsations of the entire giant star. The astronomer immediately published his alarming data on a specialized scientific forum. Other observers around the world quickly verified his findings independently. They all confirmed the same thing. The pulsation period was indeed shortening faster than expected, faster than any existing models of red supergiant evolution had predicted. But this turned out to be only the beginning of a chain of alarming discoveries. In March 2025, a team of experienced spectroscopists from the European Southern Observatory published the results of their many years of painstaking observations of Betelgeuse. They patiently analyzed the star's spectrum, light carefully broken down into its constituent wavelengths using special instruments. Each chemical element in the atmosphere of any star leaves characteristic unique lines in its spectrum. By measuring the position and intensity of these spectral lines, it is possible to accurately determine the chemical composition, surface temperature, and velocity of gas flows. The results of their many years of work turned out to be extremely unusual and alarming. The amount of heavy chemical elements in Betelgeuse's atmosphere has increased significantly in recent years. Calcium, titanium, scandium, and other heavy elements have appeared in noticeable quantities where they should not be. These elements are usually formed deep inside stars during thermonuclear fusion under extreme conditions. Under normal conditions, they should remain locked in the star's core, but now they have unexpectedly appeared on the visible surface of the giant. This could only mean one thing. Powerful convection of material was taking place inside the star. Intense mixing of matter between the hot core and the cold outer shell. Hot gas from the depths constantly rises to the surface in huge streams. Cold gas from the surface descends into the depths. Betelgeuse literally mixes its internal contents like a giant cosmic mixer. Red supergiants are indeed subject to convection, which is a completely normal natural process. Convection is one of the ways energy is transferred from the core to the surface of a star. But the intensity of the observed convection directly depends on the internal physical conditions. The more unstable the star is inside, the stronger and more intense the mixing of the layers. The spectra showed unequivocally that convection in Betelgeuse has increased catastrophically over the past few years. The team wrote very cautiously in their scientific article, "The observed changes in the chemical composition of the atmosphere are fully consistent with the hypothesis of the acceleration of the star's final evolution. Betelgeuse may well be in the very last stage of the life of a red supergiant before collapse. However, the exact time frame before a possible catastrophic collapse of the core remains extremely uncertain. Additional systematic observations and improved theoretical models are needed to refine the predictions. Cautious scientific words, diplomatic academic language, avoiding sensationalism. But anyone who could read between the lines of scientific publications understood the essence. Something fundamental is changing inside Betelgeuse every day, and these changes are happening at an alarming rate. June 2025 was the month when everything changed definitively and irrevocably. A team from the Harvard-Smithsonian Center for Astrophysics completed the creation of completely new computer models of Betelgeuse's evolution using the most advanced software codes. They carefully took into account absolutely all known physical processes inside massive stars: the rotation of the star around its axis, the constant loss of mass through stellar wind, intense convection of layers, and all stages of thermonuclear reactions. The calculations required hundreds of thousands of hours of work by the country's most powerful supercomputers. The models had to answer the one critical question that concerned everyone: how much time was left before Betelgeuse's final explosion? The results of the computer modeling were absolutely shocking to the entire scientific community. Old models created by astrophysicists several decades ago confidently predicted a completely different future. Betelgeuse was supposed to live quietly for tens of thousands of years without any particular problems. According to their calculations, the star was in a relatively stable phase of its existence. According to these outdated predictions, silicon burning in the core had not even begun yet. Ahead lay a long and predictable path of evolution leading to inevitable collapse. New models, taking into account all the latest observations and significantly improved physics of the processes, showed a completely different picture. Silicon burning is already in full swing right now at the very center of the star. The iron core is actively forming day after day, increasing in size. The whole process has unexpectedly accelerated due to the enormous mass of the star and the specific features of its complex internal structure. Convection transfers energy from the core to the surface much more efficiently than old simplified theories suggested. The core is contracting much faster than all previous estimates. Models have calculated a new timeline with frightening accuracy. From the moment silicon begins to burn actively to the final catastrophic collapse of the core, a star of this mass has only about 5 to 10 years left. 5 to 10 years before the explosion, no more. But the main problem lay in another question, to which the models could not give a precise answer. When exactly did this critical silicon burning begin in the star's core? Modern observations show only the outer layers of Betelgeuse, accessible to our telescopes. The core is reliably hidden deep inside under trillions of tons of hot gas. But all the observed changes, the shortening of the pulsation period, changes in the chemical composition of the atmosphere, massive loss of matter, all this unambiguously pointed to one thing. The process is already in full swing. If the burning of silicon began about 3 years ago, humanity has between 2 and 7 years of observations left. If it began 5 years ago, we may have only months left before disaster strikes. The team of astrophysicists did not rush to publish such shocking results immediately in the open press. They wanted to carefully double-check every aspect of their calculations and make sure they were reliable. Such a sensational statement required absolute certainty in every figure. It was impossible to frighten billions of people around the world without solid scientific grounds. But someone within the research team strongly disagreed with the policy of silence. This person decided that the public had an unconditional right to know the truth immediately. In July 2025, an anonymous leak appeared on a specialized scientific forum. Someone posted a file containing all the results of the secret simulation, including detailed timeline charts. The accompanying comment to the file was extremely brief and alarming. This is not a drill or scaremongering. Betelgeuse is in the very last stage of its existence right now. We may indeed have only a few years left, or perhaps even less time. The public has an absolute and indisputable right to know this truth. The scientific forum literally exploded with activity within hours of the publication. The file with the models spread instantly across the internet like wildfire. Astronomers around the world immediately downloaded the data and began checking it. Some researchers found minor errors in individual assumptions of the model. Others fully confirmed the main results with their independent calculations. A heated debate began in scientific circles. One research group from Germany recalculated all the models with slightly different initial parameters for the star. Their calculations yielded a slightly longer evolutionary timescale, 10 to 20 years, rather than 3 years. Another group of astrophysicists from Australia took into account additional complex effects of the star's rapid rotation around its axis. Their model showed an even shorter and more frightening timescale, only 2 to 4 years before the explosion. It was not possible to reach a scientific consensus due to the complexity of the problem. But absolutely all researchers agreed on one fundamental conclusion. The time frame before the explosion has shortened sharply and dramatically. It has shortened significantly compared to all previous estimates. Betelgeuse will definitely explode not in tens of thousands of years, as previously thought. The explosion will occur in a few years, or at most a few decades, but definitely not in millennia. We will all be alive when it finally happens before our eyes. Our generation will witness it, and perhaps the next generation will too. But it will happen incredibly soon by any cosmic measure of time. The media instantly picked up on the sensational story and spread it around the world. Dramatic headlines returned to the front pages of newspapers and news sites. Betelgeuse is preparing for its final explosion right now. Scientists predict a supernova in the next few years. The end of an era is closer than ever. The astronomical community was divided into two opposing camps on this issue. Some called for maximum scientific caution and restraint in statements. Computer models always contain inaccuracies and simplifications of reality, they said. There are too many unknown variables and uncertainties in the calculations. One cannot make such bold and frightening statements based solely on computer simulations that are not confirmed by direct observations. Other scientists objected, saying that the observed data is absolutely clear and speaks for itself. The changes in the star's behavior are very real and continue to grow. We have a duty to be honest with the public and prepare for the inevitable. August 2025 brought new dramatic evidence of the approaching catastrophe. The James Webb Space Telescope received special permission to point its powerful instruments at Betelgeuse. Infrared observations with unprecedented high resolution allowed us to see what was previously impossible. The goal was to study the surface of the giant star in detail, to see convection cells the size of planetary orbits, to accurately measure the temperature of different regions of the surface, and to find any signs of critical instability. The images from the telescope arrived after a week of tense anticipation, and the astronomers studied them in absolute silence. What they saw in these images fully confirmed all their worst fears and predictions. The visible surface of Betelgeuse was literally covered with huge, irregularly shaped dark spots. These were not small formations similar to the usual sunspots on our sun. Each spot was gigantic, comparable in size to the Earth's orbit around the sun. Dozens of such giant dark areas covered almost half of the star's entire visible surface at the same time. Dark spots on the surface of stars are relatively cold regions with lower temperatures. These are areas where the temperature is significantly lower than the surrounding hot atmosphere for various reasons. They form where powerful convection brings colder material from the deeper layers to the surface, or where strong magnetic fields temporarily suppress the normal flow of energy to the surface. But such an incredible number of spots at the same time on one star, and of such gigantic size? This was an absolutely unprecedented phenomenon in the entire history of observations. The James Webb Telescope science team wrote the following very cautiously in their official report. The observed extreme activity on the visible surface of the star clearly indicates a state of extreme instability of the entire internal structure. Betelgeuse is definitely in a physical state that could well precede the final catastrophic collapse of its core. However, without the ability to directly observe the processes in the star's core, accurate time predictions remain fundamentally impossible. They did not give a specific figure of 3 years before the explosion. They did not give an exact date for the expected catastrophe. But one word in their conclusion, precede, spoke volumes to those in the know. September 2025 brought another alarming event in this drama. Betelgeuse began to dim noticeably again for observers around the world. The dimming was not as dramatic or profound as in the infamous year 2019, but it was definitely noticeable even to the naked eye. The brightness dropped by about 20% in just 2 weeks of continuous observation. Astronomers immediately sprang into action and activated all available instruments. Was this another massive cold dust ejection, like last time? Or was something completely different and more serious happening this time? Detailed spectroscopy quickly revealed something unexpected. This time, there was no dust in the surrounding space. The dimming was a completely real physical process on the star itself. Betelgeuse was indeed emitting significantly less light into space than usual. The temperature of the visible surface dropped significantly in all measurements. The star was literally cooling down before the eyes of astonished observers. Why would a red supergiant suddenly cool down without any apparent external causes? This can happen when internal thermonuclear processes temporarily slow down for some reason, when the flow of energy from the hot core to the surface becomes less efficient, when the star begins to actively redistribute energy within itself, preparing for something important. The cooling period lasted exactly 3 weeks under the close attention of astronomers. Then, the brightness slowly began to return to normal values. By October of the same year, the star had completely returned to its usual luminosity, as if nothing had happened. But astronomers noticed one critically important detail in the observation data. The star's spectrum had changed noticeably during this cycle of cooling and heating. The spectral lines of some chemical elements became significantly stronger and brighter. The lines of other elements weakened noticeably or almost disappeared. The chemical composition of the star's visible atmosphere had definitely shifted toward heavier elements. More oxygen appeared in the spectra, and more silicon became visible on the surface. These are elements from the very deep inner layers of the star, where advanced stages of thermonuclear fusion are taking place. Powerful convection continued to relentlessly carry them upward from the depths. The star literally showed us its inner contents through changes in its spectrum. October 2025 became the month of the scientific community's organized response. An international group of astronomers from dozens of countries organized a large-scale coordinated campaign of continuous observations. The project was officially named Betelgeuse Watch, Continuous Observation of Betelgeuse. Telescopes around the globe joined the program: optical instruments, infrared observatories, radio telescopes. Every night, someone somewhere on the planet observes Betelgeuse and records the data. The information is collected centrally in real time via the internet. Any slight changes in the star's behavior are recorded almost immediately. The main goal of the project was crystal clear: not to miss the next critical stage of evolution. If Betelgeuse is indeed on the verge of exploding, there must be some precursors to the catastrophe. Sudden changes in the star's brightness, dramatic changes in spectral lines, anomalies in the pulsation period. Something is bound to happen that will tell scientists that it is happening right now, at this very moment. November and December passed in tense anticipation and continuous observation. Data streams arrived daily from all continents. Betelgeuse's brightness remained relatively stable without any sudden jumps. The pulsations continued with an established period of about 320 days. The spectrum showed slow, gradual changes, but nothing truly dramatic was happening. The star behaved surprisingly calmly and predictably. Astronomers began to relax a little after months of tension. Perhaps all the panic of the past few months had indeed been premature and unfounded. Perhaps humanity really did have decades of peaceful observation ahead of it. Perhaps the computer models had been seriously mistaken in their gloomy predictions after all. And then January 2026 arrived, and everything changed forever. On January 3rd, an experienced astronomer in Chile, working as part of the international Betelgeuse Watch campaign, recorded an extremely unusual and alarming change. Betelgeuse's brightness suddenly increased sharply without warning. In just 6 hours of continuous measurements, the brightness increased by a full 10% from its normal value. This was definitely not the usual slow pulsation of a star stretched out over weeks. Pulsations always occur slowly and smoothly, without sudden jumps. This was something completely different, a sharp, rapid, and unexpected change. He immediately notified the entire global network of observers via secure communication channels. Other telescopes in different parts of the planet quickly focused on the star for confirmation. All independently confirmed the same thing. The brightness had indeed increased sharply and continued to rise slowly. By the end of the first night of observations, Betelgeuse had become 15% brighter than its usual state. What exactly is happening to the star at this moment? Some kind of sudden burst of activity? Red supergiants do sometimes exhibit sudden bursts of brightness. Powerful convective processes deep inside can suddenly bring particularly hot material to the visible surface. The surface temperature rises temporarily, and the overall luminosity increases sharply for a short time. Spectroscopic observations began immediately around the world. Teams of astronomers carefully analyzed the incoming light, looking for any changes. They searched for clues to understanding the processes taking place. The spectra revealed important details. The temperature of the star's visible surface had indeed risen significantly. Not by much in absolute terms, only a few hundred degrees. But for such an incredibly large star, even a relatively small change in surface temperature means a huge change in the overall luminosity of the entire object. The spectral lines also showed an active ejection of material into the surrounding space. The hot gas moved outward from the star at impressive speeds of tens of kilometers per second. Betelgeuse was actively ejecting its matter into the cosmic void. The brightness flare lasted exactly 12 hours under the close observation of telescopes. Then the brightness began to slowly fall back to normal. By the next night, the star had almost returned to its usual calm state. One astronomer commented on the incident in a closed project forum quite vividly. "It's like a giant hiccup," he wrote. The star suddenly hiccuped, ejecting a portion of energy and material outward. Then it quickly calmed down and returned to normal. This is a perfectly normal process for a critically unstable dying star. But another project participant immediately responded more gloomily. "Hiccups are often a symptom of something more serious, not just a harmless phenomenon. Betelgeuse is clearly showing us that powerful processes are taking place inside it that we cannot see directly. And these hidden processes are becoming more and more intense with each passing week." On January 8th, a second flare occurred, noticeably stronger than the first in all respects. The brightness increased sharply by 25% over 8 hours of continuous measurements. Spectra showed the release of even larger volumes of hot gas into space. The speed of the material flow reached 50 kilometers per second, according to Doppler measurements. On January 15th, a third flare of approximately the same power occurred. On January 22nd, observers recorded a fourth burst of activity. A distinct pattern began to emerge in the observation data. A certain periodicity of events became apparent. Approximately every 7 days, Betelgeuse flares up sharply brighter than usual. It ejects a significant amount of energy and matter. Then it quickly calms down until the next cycle. These were definitely not random, chaotic events with no connection. It was a clear rhythm, repeating with almost mathematical precision. Something deep inside the star was working with a periodicity of about 1 week. But what exactly? Theories began to multiply among researchers. Could it be related to the rotation of the superdense iron core around its axis? Or periodic large-scale convective upheavals in the deep layers? Or pulsations of some intermediate shells between the core and the surface? No one knew the correct answer to these questions, but everyone understood one thing. This was completely new behavior for the star. Betelgeuse had never shown anything like this before in the entire history of observations. Something fundamental and irreversible had changed in its internal structure. January 27, 2026, will be remembered as the day of the most powerful flare. Its brightness shot up to 40% above normal in a matter of hours. Betelgeuse became brighter than ever before in modern documented history. It temporarily surpassed Rigel in brightness, usually the brightest star in the entire Orion constellation. And then something happened that made astronomers around the world literally freeze in front of their monitors. At the absolute peak of this flare, the spectra showed the appearance of a completely new bright line. A strong emission line of the chemical element nickel was clearly visible in the data. Nickel in the atmosphere of a red supergiant has a very specific meaning. This element is formed during the radioactive decay of cobalt under special conditions. Cobalt, in turn, is created from iron in advanced nuclear reactions at extreme temperatures. The presence of nickel in the visible atmosphere of a star means only one critically important thing. The nuclear processes of heavy element synthesis are no longer confined to the central core. They are actively occurring in the expanded shells around the core. The layers of the star above the iron core have become hot and dense enough for the synthesis of such heavy elements. This is a sign of a very late, critically advanced stage in the evolution of a massive star. A very late stage when the iron core is already fully formed and growing, when thermonuclear burning continues only in the thin shells above the dead core, when the star has literally exhausted its last available resources to sustain life. The team of spectroscopists immediately published an urgent scientific message to the entire community. The detection of nickel in Betelgeuse's atmosphere clearly indicates a very advanced stage of nuclear burning inside. The star may well be much closer to the final collapse of its core than even the most pessimistic predictions suggested. It is strongly recommended that the intensity of continuous monitoring be maximized by all available means. The phrase "closer than expected" was a diplomatic scientific way of saying something frightening. It could happen at literally any moment now, and we must be absolutely prepared. February 1st, 2026 was the day the seriousness of the situation was officially recognized. NASA held an emergency press conference, broadcast live around the world. The director of the agency's astrophysics division appeared before a conference room filled with journalists and cameras from dozens of television channels. He began his speech with the most honest acknowledgement of what was happening. "We have been observing absolutely unprecedented changes in the behavior of the red supergiant Betelgeuse in recent months. The star is showing multiple signs of critically accelerated final evolution before an explosion. Based on the most advanced computer models and the latest detailed observations, the scientific community has reached the following consensus. Betelgeuse is definitely in the very last stage of a red supergiant's life before collapse. A supernova explosion is absolutely inevitable in the foreseeable future. The question is no longer whether it will happen someday. The only question now is when exactly it will happen." One of the journalists immediately asked the most obvious and important question: "When? Can you give a specific date or at least an approximate range?" The director took a deep breath before answering, clearly understanding the importance of his next words. "Unfortunately, we cannot give an absolutely accurate date for the explosion for objective reasons. The physics of the final collapse of a star's core is incredibly difficult to model. There are too many critical variables and uncertain parameters. But based on all the observable characteristics of the star and our best theoretical models, we estimate a timescale of several months to several years at most. Perhaps the process will stretch to 10 years in the most optimistic scenario. But we definitely do not rule out the possibility that the explosion could happen significantly earlier than these estimates. A few months before the explosion in the worst case. Maybe a few years in the best case scenario. Maybe it will happen literally tomorrow morning." The whole world heard this official statement, and the world began to change rapidly after these words. The public reaction was instantaneous and swept across all areas of life. Within hours of the NASA press conference ending, the news had spread to literally every corner of the planet. Every television channel interrupted its regular programming for emergency broadcasts. Every news website posted screaming headlines on their front pages. Every social network exploded with millions of discussions and reposts. Betelgeuse will explode in the near future, possibly very soon, possibly within our lifetime. People took to the streets en masse on warm January evenings around the world. They looked up at the winter constellation Orion, slowly rising above the horizon. They searched for the distinctive reddish star in the left shoulder of the legendary hunter. They pointed it out to each other with their fingers. They took pictures with their phones and cameras. "There it is," they said to each other excitedly. "The very star that will soon change our sky forever. The star that is dying right now before our eyes as we watch it." Some people felt real fear about the unknown future. Internet forums quickly filled with anxious questions from millions of concerned people. How dangerous is this for life on Earth? Will the deadly radiation from the explosion reach us? Could our planet perish in this catastrophe? Scientists patiently continued to reassure the alarmed public through all available channels. 600 light-years is a perfectly safe distance from any supernova explosion. A supernova at such a distance from us will cause no real harm to our planet. Gamma radiation and streams of high-energy cosmic rays will be significantly scattered in interstellar space. By the time they finally reach the vicinity of Earth centuries later, they will be quite weak. Our dense atmosphere will reliably protect all life on the surface. The only real effect for Earthlings is an unusually bright light in the sky. Months or even years of abnormally bright night skies across the planet. But this light is absolutely harmless to life, not deadly to organisms. Just an incredibly beautiful, slightly frightening, and historically unprecedented cosmic spectacle. Other people, on the contrary, were genuinely enthusiastic about the prospects that were opening up. "This is the greatest astronomical event in the history of human civilization," they exclaimed on forums. a supernova explosion visible to the naked eye from Earth at a distance sufficient for safe, detailed study. All telescopes around the world and in orbit will be simultaneously pointed at Betelgeuse. Scientific data will pour into databases in incredible streams. We will learn more about the fundamental physics of massive stars in a few months of observing the actual explosion than we have learned in all the previous decades of purely theoretical research and computer modeling. Travel companies around the world have quickly begun offering specialized tours for enthusiasts. Exclusive trips to remote locations with perfectly dark skies, free of light pollution. Professional observatories in the mountains, endless deserts, remote islands in the ocean. See the supernova explosion with your own eyes in the best conditions, an event that happens once in 1,000 years. Book your seats now before they're gone. Astrologers and various mystics around the world immediately declared the event to be significant. It is a cosmic sign of change, they proclaimed in their publications. The end of an old era of humanity and the beginning of a completely new era of consciousness. The death of an ancient star symbolizes the coming transformation of all human society. We are collectively entering a new age of enlightenment and spiritual growth. Religious groups of various denominations interpreted the event in their own way. Apocalyptic sects predicted the imminent end of the world and the second coming. More moderate believers saw the event as a divine message to humanity. God reminds us of the greatness of His creation through the cosmos, of the incredible fragility of any existence in the universe, of the need to cherish every moment of life given to us. The world was rapidly divided into those who awaited the event with sincere impatience and those who awaited it with deep anxiety. Meanwhile, Betelgeuse continued its slow dance of inevitable death in the sky. February 2026 brought a continuation of disturbing changes in the behavior of the dying star. Periodic bursts of brightness continued with frightening regularity, approximately every 7 days. Regularly, like the work of a precise cosmic clock. But the intensity of each subsequent flash grew steadily from cycle to cycle. Each new flash was noticeably stronger than all the previous ones in all measurements. The brightness increased more and more each time. The ejections of hot material into space became more and more powerful and intense. By mid-February, astronomers noticed another critically important detail in the accumulated data. Between periodic flares, the star no longer returned completely to its original base brightness. Betelgeuse's base luminosity was slowly but steadily increasing regardless of the flares. Each week, the star became slightly brighter in its calm state than it had been a week earlier. A detailed graph of the change in brightness over time showed a characteristic stepwise increase in luminosity, a sharp flash upward, then a relatively rapid drop in brightness. But the drop did not stop at the previous low level, but noticeably higher. A brief stabilization at a new, higher baseline luminosity. Then, the next powerful flash started a new cycle, and again, the same pattern repeated itself. The star seemed to be slowly rocking before a decisive leap. It gained energy cycle after cycle. It was preparing for something grand and final. February 21st brought the publication of an unusual study by a team of astrophysicists. They published the results of a complex analysis of neutrino fluxes from the direction of Betelgeuse. Neutrinos are incredibly tiny elementary particles that hardly interact with the ordinary matter around them. They are born in nuclear reactions deep in the cores of all stars and instantly fly through the entire thickness of the star to the outside. Ordinary light takes years to travel from the core to the surface through dense layers. Neutrinos fly out of the core almost instantly without delay. Special neutrino detectors on Earth are capable of catching these elusive particles, very rarely with minimal efficiency, but they can catch them. Solar neutrinos are constantly recorded by detectors. Millions of these particles pass through every person every second of their lives. But neutrinos from other distant stars are recorded extremely rarely. Cosmic distances are too vast even for these penetrating particles, except in special cases of supernova explosions in relative proximity. When a massive star finally collapses, its core ejects an incredible amount of neutrinos in seconds. A real neutrino explosion always precedes a light explosion by several hours. Neutrinos fly out of the collapsing core immediately. The light flash breaks through the massive outer layers noticeably later. If Betelgeuse explodes in the near future, Underground neutrino detectors around the world will definitely record a powerful surge several hours before we see the light flash with the naked eye. A Tokyo research team has carefully analyzed all the data from the Super Kamiokande detector over the past few months. This is a huge reservoir with 50,000 tons of ultra-pure water deep underground in the Japanese mountains. The tank is surrounded by thousands of highly sensitive photodetectors that capture the faintest flashes of light. They looked for any anomalous events in the data, unusual signals that could indicate neutrinos arriving from the dying Betelgeuse. The team detected 3 suspicious events over the past 2 months of intensive observation. The events did not match the usual stable background from the sun and the atmosphere. The signals were weak, barely distinguishable above the noise level, but the estimated direction of arrival of these particles roughly coincided with the position of Betelgeuse in the sky. 3 events in 2 months is statistically insufficient for any firm scientific conclusions. They could well have been simply random fluctuations in the natural radiation background. But the team still wrote the following in their publication. If these events really are neutrinos from Betelgeuse, this could indicate a significant increase in nuclear processes inside the star. We strongly recommend that all neutrino detectors around the world begin continuous monitoring of the direction of Betelgeuse in the near future. A powerful surge in neutrino flux will be the very first reliable warning of the beginning of the final collapse of the core a few hours before the visible explosion. All major neutrino detectors around the world immediately switched to a special high alert mode. Each recorded event was carefully analyzed by specialists in real time. Every suspicious signal was repeatedly checked using independent methods. Humanity waited anxiously for the first signal of the beginning of the catastrophe. On March 1, 2026, Betelgeuse flared up again, but in a completely different way. This time, the flare was radically different from all previous cycles. The brightness skyrocketed not by the usual 40% above normal, but by an incredible 80%. The star literally doubled its luminosity in just 10 hours of continuous observation. Astronomers around the world stared at their monitors in shock at what was happening. Detailed spectra showed truly enormous emissions of hot material into the surrounding space. The gas outflow velocity reached 100 kilometers per second according to accurate Doppler measurements. The temperature of the visible surface jumped up by a whole 1,000 degrees instantly. This was no longer a simple hiccup of a dying giant as before. It was a real powerful burst of activity, although not a final catastrophic explosion. The flare lasted a record 18 hours straight, longer than any previous cycle, and when the brightness finally began to slowly fall back, it did not return to its previous baseline level. The luminosity stabilized at 50% above the star's normal state. Betelgeuse became noticeably brighter than Rigel, usually the brightest star in the entire Orion constellation. Brighter than it had ever been in the entire modern documented history of human astronomical observations. And the star clearly had no intention of calming down after this event. March 3rd brought another powerful flare of approximately the same incredible strength. The brightness again doubled from the new baseline. Now Betelgeuse was shining about 2.5 times brighter than its normal state. It was almost equal in brightness to the magnificent Sirius, the brightest star in the entire night sky on Earth. People around the world began to notice the difference, even with the naked eye, without telescopes. The familiar constellation of Orion looked strange and wrong in the winter sky. The red star in the hunter's shoulder suddenly shone noticeably brighter than the blue star Rigel in his foot. The entire constellation looked visually unbalanced and geometrically incorrect. It seemed alien and disturbing to observers. On March 8th, the third most powerful flare in a week of observations occurred. Betelgeuse finally surpassed even the bright Sirius in luminosity. It became the brightest star in the entire night sky of the planet. The brightest, except for the sun, the moon, and a few bright planets in the solar system. Ordinary people who had never been particularly interested in astronomy before suddenly began to notice the changes. What is this unusually bright red star in the sky? When did it appear there so brightly? Why didn't I notice it before? It has always been in the sky, astronomers patiently explained to concerned people. It is just that now it is slowly dying before our eyes, and its death is truly magnificent and terrifying at the same time. March 14th was the day Betelgeuse finally stopped behaving predictably. The regular 7-day flashes suddenly stopped. Instead, the flashes began to occur completely chaotically and unpredictably. Every few days there was a new flare. Sometimes 2 powerful flares occurred in one day. Sometimes there was a week-long break with no activity. It became absolutely impossible for observers to predict the next flare. The brightness of the star varied chaotically over a wide range from 2 to 4 times higher than normal luminosity. Betelgeuse literally trembled and convulsed in the sky. It desperately fought against the inexorable gravity with all its remaining strength. It fought for the last precious moments of its million-year life before the inevitable end. Detailed spectroscopy revealed a dramatic picture of what was happening inside. Betelgeuse's outer atmosphere was literally being torn apart by internal forces. Huge masses of hot gas were continuously escaping into the surrounding space from all sides. The ejection velocity reached 200 kilometers per second according to measurements. The star was losing its matter at an incredible rate of decay. In 1 week, it ejected into space a mass of matter equivalent to several entire planets the size of Earth. The clouds of ejected gas around the dying star began to glow actively with their own light. They were heated by powerful radiation from the central source. They were ionized by the action of harsh ultraviolet light. They slowly formed an extensive luminous nebula even before the final explosion. Betelgeuse methodically surrounded itself with a funeral shroud of its own flesh and blood. March 20th brought the discovery of another alarming change in the behavior of the dying giant. The period of rotation of the entire star around its axis had changed significantly in recent weeks. Previously, Betelgeuse rotated incredibly slowly, as is typical for red supergiants. One complete rotation around its axis took several Earth years. Red supergiants are lazy and slow in their movements. Their monstrous size and relatively weak magnetic fields do not contribute to rapid rotation, but careful measurements of the Doppler shift of spectral lines showed a definite acceleration in rotation. The edges of the star's visible disk were moving noticeably faster relative to the center than a month ago. Betelgeuse slowly spun around its axis day after day. Why was this happening now? The outer shell of the star continued to expand outward as it should. It did not contract and could not cause the acceleration of visible rotation. But deep inside, hidden from our eyes, the iron core was rapidly collapsing under its own weight. It was losing size with every passing hour, compressing more and more. And the fundamental law of conservation of angular momentum required an acceleration of rotation during compression. Just like a figure skater spins faster and faster when they press their arms against their body. Betelgeuse's core was inexorably shrinking in size and at the same time spinning faster and faster. On March 25, 2026, NASA held its second emergency press conference in 2 months. The director of the astrophysics department looked noticeably tired and aged. He clearly hadn't slept properly for weeks. None of his team had slept enough. Everyone had been watching Betelgeuse day and night. He began his speech with an honest acknowledgement of the reality of the situation. Over the past 3 weeks, Betelgeuse has exhibited behavior that goes far beyond any previous observations of red supergiants in history. The star is in a state of extreme critical instability right now. Based on all the current data, we have been forced to revise our time estimates once again. The final collapse of the core could happen at literally any moment now, from a few days to a few months at most. We are physically unable to predict anything more precise than this range. One journalist asked a logical question that concerns millions of people. How exactly will we know when the explosion begins? Will humanity have any advance warning? The director answered this critically important question as clearly and thoroughly as possible. The global network of neutrino detectors will give us a warning several hours before the light flash from the explosion reaches the visible surface of the star. When the iron core finally collapses inside, the neutrinos will fly out from the center almost instantly. It will take a noticeable amount of time for light to break through the massive outer layers of the dying star, from several hours to a whole day, depending on the details of the structure. We have created an automated global system for immediately notifying all interested parties. When underground detectors record a characteristic neutrino burst from the direction of Betelgeuse, we will instantly notify the entire astronomical community and the general public through all channels. People around the world will have enough time to prepare themselves mentally, to go outside under the open sky, to point their cameras and telescopes, to witness the greatest cosmic event in the history of civilization. Prepare to witness the death of a star, a strange and yet perfectly fitting phrase. A global automatic alert system was carefully designed and tested. The supergiant detector in the mountains of Japan constantly monitored the sky. The AI cube detector deep under the ice of the South Pole worked continuously. Detectors in Canada, Italy, China, and other countries were all connected to a single network. When any two independent detectors simultaneously recorded a powerful neutrino burst from Betelgeuse within 1 minute of each other, the automatic computer system immediately sent out emergency alerts. To astronomers around the world, all observatories, space telescope operators, the media, and ordinary people. And to all those millions of enthusiasts who have specifically signed up for push notifications about the event. Special mobile apps were released for all platforms and operating systems. Supernova Alert, real-time supernova alerts. The apps were downloaded by tens of millions of people around the world in a matter of weeks. Ordinary people wanted to know immediately when it happened. They wanted to be absolutely ready for the greatest spectacle of their lives. April 1st, 2026, was the day when everything really changed forever. Astronomers around the world suddenly noticed something completely new in the continuous observation data. The base brightness of Betelgeuse, which had been fluctuating erratically in recent weeks, suddenly began to rise steadily, without stopping. There were no more cycles of flare-decline stabilization as before. Only a continuous, steady increase in luminosity hour after hour, without interruption. By the evening of April 1st, Betelgeuse was shining about 5 times brighter than its usual normal state. It completely eclipsed all the stars in the night sky, including the majestic Sirius. Only the bright Venus in the evening sky still surpassed it in luminosity. The constellation Orion looked completely unrecognizable against the familiar patterns of stars. The red star in the hunter's shoulder shone so brightly that it literally dominated the entire constellation. Spectroscopic data showed a completely incredible picture of the processes taking place inside the dying star. The temperature of the visible surface skyrocketed by several thousand degrees at once. The speed of the ejection of hot material into the surrounding space reached 300 kilometers per second. The lines of heavy elements in the spectra became stronger and more noticeable with each new measurement. Nickel, cobalt, titanium, and other products of deep thermonuclear reactions now dominated the star's atmosphere. Astronomers understood that they were observing something fundamentally final and irreversible in the life of the giant. These were no longer temporary fluctuations or reversible processes as before. The star had finally lost its internal stability and began an irreversible fall into the abyss of collapse. On April 3rd, the brightness continued to grow inexorably day after day without the slightest sign of slowing down. Betelgeuse reached a luminosity about 8 times higher than normal, according to accurate measurements. It now shone brighter than any object in the night sky except the moon in its various phases. People began to notice that they could easily distinguish large objects on the street only thanks to the reddish light of this single star. There was no need for flashlights or street lighting on moonless nights. Betelgeuse itself illuminated everything around it brightly enough. Neutrino detectors around the world operated at maximum sensitivity around the clock. Physicists continuously analyzed every recorded event in real time through secure channels. They searched for the characteristic pattern of a powerful burst of particles from a dying star, the first signal of the beginning of the final catastrophic collapse of the iron core deep inside. April 10th brought news that caused the astronomical community to literally freeze in anticipation. The team from the Japanese supergiant detector recorded a short series of suspicious events early in the morning. 5 events in 15 minutes of continuous observation, all with an estimated direction of arrival approximately from the position of Betelgeuse in the sky. The statistics were still not convincing enough for absolute certainty, but they were alarming. The Canadian detector independently confirmed the detection of 2 anomalous events at approximately the same time. It could have been just a random fluctuation in the natural background radiation of the atmosphere and space, or it could have been the first faint hint of a coming catastrophe in the bowels of the star. The scientific team decided not to raise a global alarm based on such a weak signal. The criteria for automatic notification required a much stronger and more unambiguous surge in activity. Dozens or hundreds of events per minute from two independent detectors simultaneously. But they immediately notified a small circle of colleagues via secure communication channels. "Be extremely vigilant now," they wrote in urgent messages. The situation could resolve itself at any moment without further warning. On April 14th, Betelgeuse reached a brightness 12 times higher than its normal state. It was now brighter than a crescent moon in the night sky, according to objective measurements of luminosity. Bright enough to cast clear, distinguishable shadows from objects onto the illuminated Earth. People around the world stood in the streets on warm April evenings and looked up in reverent silence. The red star blazed in the constellation Orion like a cosmic beacon of death and transformation. Majestic, and at the same time deeply frightening in its anomalous power. The night sky of Earth had never looked so strange and alien in all of documented human history. A single star dominated the entire sky with its disturbing red light. The constellations looked distorted and wrong because of this dominant source. Everything seemed unnatural and temporary, as if reality had shifted slightly from its usual place. April 15th, 2026, began as a relatively normal day for most people. The sun rose above the horizon in the morning, as it had done for millions of years. People woke up, ate breakfast, and drove to work through crowded city streets. Life continued at its established pace, despite the anomalous star in the sky. Telescopes around the world continued their continuous observations of Betelgeuse methodically and patiently. Neutrino detectors deep underground and under the ice continued to record events continuously. Everything seemed relatively normal in the usual sense of the word. And then, at 1437 UTC, what all of humanity had been waiting for happened. The Super Kamiokande detector suddenly registered an absolutely incredible surge in neutrino activity simultaneously. Not 5 events in 15 minutes, as had been the case a week ago. 187 separate events in 1 minute of continuous data recording. All events with a calculated direction of arrival precisely from the position of Betelgeuse in the sky. The statistical significance of the detection exceeded 10 sigmas. Absolute mathematical certainty in the reality of the signal. Exactly 42 seconds after the start of the Japanese surge, the ice cube detector at the South Pole recorded its own powerful surge of activity. 114 events in 1 minute, all from the direction of the Orion constellation. The delay time between the detectors corresponded exactly to the time it took for the information to travel through secure internet channels. The automatic computer system immediately activated according to a carefully programmed algorithm. 2 independent detectors simultaneously recorded a powerful surge from the same source. The criteria for a global alert were met without a doubt. 8 seconds after confirmation from the second detector, the system began sending out mass emergency alerts. Millions of people around the world suddenly felt their cell phones vibrate and beep simultaneously. The special Supernova alert app was automatically activated on all installed devices. A loud warning pierced the silence of offices, cafes, streets, and homes across the planet. Screens lit up in bright red with large text displaying the message. Critical astronomical event. Neutrino flash from Betelgeuse detected. Final collapse of star's core has begun. A visible light flash from the supernova is expected within 12 to 24 hours. It is recommended to observe the constellation of Orion after sunset. The world literally stopped for a few long moments in a state of collective shock. It happened. It really started right now. The star is dying at this very moment, and we will all witness it. People ran out of office buildings onto the streets, leaving their work unfinished. Drivers stopped their cars in the middle of the road and got out, blocking traffic. Students left university lecture halls, ignoring their professors' protests. Workers threw down their tools in factories and plants. Everyone wanted to be outside under the open sky when it happened. Everyone wanted to see with their own eyes the greatest cosmic event in the history of civilization. The media immediately interrupted all regular programming for emergency news broadcasts. Every television channel around the world switched to live coverage from observatories. Cameras were trained on the constellation Orion, slowly rising above the eastern horizon as evening approached. Betelgeuse was already bright enough to be visible even in bright daylight, a red dot in the blue sky. But the real spectacle was to begin after the sun set below the horizon. Astronomers around the world immediately pointed all available telescopes at the dying star in unison. The James Webb Space Telescope interrupted its planned observations of distant galaxies and turned its gaze to Betelgeuse. The Hubble telescope, the Chandra X-ray Observatory, all space-based instruments, all focused on a single point in the sky. Ground-based observatories prepared their instruments for a night of continuous measurements. The largest coordinated observation campaign in the history of astronomy began at that moment. Neutrinos continued to arrive on Earth in a powerful stream for the next 2 hours straight. Detectors around the world recorded thousands of events every minute without interruption. It was indeed the characteristic burst predicted by all theoretical models of core collapse. The iron core of Betelgeuse was rapidly collapsing under its own weight right now, in real time. Protons and electrons in the core were merging together, forming neutrons and ejecting an incredible number of neutrinos outward. A neutron star was being born in the very heart of the dying giant at this very moment. And the outer layers of the star, deprived of the support of pressure from within, began their catastrophic fall inward toward the collapsing center. By 4 p.m. UTC, the neutrino flux began to slowly weaken and diminish. By 5 p.m., it had fallen to the background level of the detectors completely. The collapse of the core was finally completed during these few hours of activity. A neutron star was born and stabilized in the center of Betelgeuse. Now the next phase of the catastrophe began. Trillions of tons of superheated gas from the outer layers of the star collapsed inward toward the superdense core at incredible speeds. The matter fell faster and faster, accelerating under the influence of monstrous gravity. Tens of thousands of kilometers per second was the calculated speed of fall. Absolutely all of the star's matter was rushing toward the center at the same time. And then all this unimaginable volume of matter hit the surface of the newborn neutron star almost simultaneously. The collision occurred with a force that the human mind is physically incapable of truly comprehending. Matter rebounded from the superdense core at the same incredible speed. A powerful shock wave formed in this collision and began its journey outward through the layers of the star. It swept through the entire remaining mass of the giant, heating the gas to billions of degrees instantly. Thermonuclear reactions of explosive fusion flared up in this hell of temperatures and pressures. All the chemical elements of the periodic table were created in seconds in the fire of the explosion. The shockwave took time to travel from the collapsing core to the visible surface of the star. Betelgeuse is incredibly large. Light takes several hours to travel from the center to the surface. The shockwave moved slower than light, albeit at tremendous speeds. Astronomers expected the light flash to reach the surface approximately 12 to 24 hours after the core began to collapse. Humanity waited in tense, silent anticipation of the greatest spectacle of all time. The sun slowly set behind the western horizon in different time zones around the planet. Twilight gradually painted the sky in deep shades of purple and red. The first bright stars began to appear one after another in the darkening sky. And among them, high above the eastern horizon, Betelgeuse burned brighter than any other star. The red beacon of the dying star dominated the entire night sky of the planet. Billions of people around the world stood in streets, parks, on rooftops and balconies. They looked up at this bright red dot of light in the constellation Orion. They waited for the moment when it would flash brighter than 1 billion suns at once. Telescopes and cameras were pointed upward everywhere. Professional astronomers in observatories, amateurs with equipment in their backyards, ordinary people with simple smartphones, all ready to capture history. The hours dragged agonizingly slowly in this tense anticipation of the unknown. 20 hours had passed since the neutrino was detected, but Betelgeuse's brightness remained stable with no visible changes. 22 hours, still no changes in the telescope data. 23 hours of waiting under the open sky. And then, at 13:42 on April 16th, Universal Time, Exactly 23 hours and 5 minutes after the first neutrino burst was detected, something happened that changed history forever. An astronomer in Chile, who had been continuously observing Betelgeuse through a large telescope, suddenly froze in front of the monitor screen in complete shock. The brightness of the star in his detector began to increase rapidly without warning, not slowly and smoothly, as in the last weeks of observation. Incredibly fast, explosively, growing exponentially with every second of measurement. He was watching the birth of a supernova in real time, right before his eyes. The brightness doubled in the first 30 seconds after the increase in luminosity began. It doubled again in the next 20 seconds of continuous measurements, and again 15 seconds after that. An exponential growth, accelerating with each passing moment without stopping. The detector began to saturate from the excess of incoming light after a few minutes. Too many photons were hitting the sensitive matrix at once, overloading the instrument's electronics. The Chilean astronomer immediately switched to a less sensitive observation mode with short exposures. Other observatories around the world quickly confirmed his data independently of each other. Betelgeuse was indeed rapidly flashing brighter with each passing second. And on Earth, billions of people standing under the open night sky across the planet saw it with their own naked eyes at the same time. The red star in Orion's shoulder began to glow noticeably before the eyes of astonished observers. Slowly at first, barely discernible to the human eye in the first few minutes. But then faster, more obvious, more dramatic with each passing minute under the sky. 5 minutes after the flash began, Betelgeuse was already shining brighter than the full moon, according to objective measurements. 10 minutes later, it became brighter than the moon had ever shone in the entire history of observations. 15 minutes later, its brightness exceeded the sunlight on Earth at noon on a clear day. Night literally turned into day before the eyes of a shocked humanity. Red light flooded everything around with incredible intensity. The shadows from objects became sharp and clear, as if under the bright midday sun. People could easily distinguish each other's faces from hundreds of meters away. They could read small print in books without additional artificial lighting. The sky turned from black to dark red, then bright red with each passing minute. All the stars in the sky completely disappeared from view in this stream of light from Betelgeuse. Even the bright planets became completely invisible. Only the sun, hidden behind the horizon on the night side of the Earth, still surpassed the dying star in terms of radiation power. But the difference was rapidly decreasing with each passing minute of observation. The brightness continued to increase incredibly rapidly, showing no signs of slowing down or stabilizing. 20 minutes after the explosion began, Betelgeuse was shining about 50 times brighter than the full moon. Half an hour later, it was 100 times brighter than moonlight. The red glow became so intense that people began to experience physical discomfort when looking directly at the source with the naked eye. It was not dangerous discomfort, just light that was too bright for comfortable direct observation. Astronomers in observatories were forced to use special filters that weakened the light flow thousands of times. Even through powerful telescopes, direct observation became impossible without protecting the optics. The supernova was too bright for ordinary instruments designed for dim, distant objects. 45 minutes after the visible flash began, Betelgeuse's brightness reached about 1/10 of the brightness of the daytime sun. The night sky now looked like deep twilight rather than true night. A reddish glow flooded the entire planet on the side facing the constellation Orion. People on the daytime side of Earth could not see the supernova because of the bright sunlight in the sky, but they eagerly awaited nightfall to see the spectacle with their own eyes. The increase in brightness finally began to slow down about an hour after the explosion began. The exponential curve transitioned into a smoother logarithmic increase in luminosity. After an hour and a half, the brightness reached about 1/5 of the sun's luminosity and began to slowly stabilize at that level. 2 hours after the flash began, the increase stopped completely. Betelgeuse reached the peak brightness of a supernova, approximately -18 stellar magnitudes on the astronomical scale. It was about 4 billion times brighter than it was in its normal state as a red supergiant. It was about 200,000 times brighter than the full moon in the Earth's sky. Approximately 1/5 of the brightness of the daytime sun, according to objective photometric measurements, bright enough to be clearly visible even in bright daylight against the blue sky, a red dot hanging next to the yellow disk of the sun during the day. At night, it turned night into day with its powerful reddish light. Humanity stood under this incredible light in reverent silence and awe. Many cried from overwhelming emotions, awe, fear, joy, and sadness all at once. It was too big, too powerful, too beautiful for ordinary human emotions. Space showed its true face, majestic, indifferent, stunningly beautiful, and deeply frightening at the same time. We witnessed the death of a star with our own eyes in real time. An event that happened 600 years ago in distant space had finally reached our planet. The light had traveled through the emptiness of interstellar space for 6 centuries, and now it was here, flooding the Earth with the fire of a dying giant's final farewell. Betelgeuse no longer existed as a star in the usual sense of the word. Instead of a red supergiant, there was now an expanding cloud of hot gas, the remnant of a supernova. At the very center of this cloud, a newborn neutron star the size of a small city was spinning. Super dense, incredibly hot, emitting powerful streams of particles and magnetic fields. A pulsar, a cosmic beacon that will shine for thousands or millions of years into the future. And around it, a cloud of material expanded at speeds of tens of thousands of kilometers per second. Oxygen, carbon, iron, silicon, and all the other elements created in the fire of the explosion. Enough material to form thousands of planetary systems in the future. Enough building blocks for new life to emerge somewhere in the galaxy millions of years from now. Betelgeuse died, but its death was also the birth of something new. April 17, 2026 began under a red sky all over the world. The supernova continued to shine with the same incredible brightness as when it reached its peak. People who had spent the whole night outside under the open sky slowly dispersed to their homes, exhausted. They had seen the greatest spectacle of their lives, but reality demanded a return to their usual affairs. Work awaited, and responsibilities had not disappeared because of the cosmic drama in the sky. But the world would never be the same after this night of observation. The daytime sky looked completely surreal and wrong for human perception. The yellow sun shone on one side of the sky as it had done for millions of years. The red dot of Betelgeuse blazed on the other side of the same sky. 2 stars in the same sky at the same time, a sight that no one in the history of civilization had ever seen before. The red dot was noticeably dimmer than the yellow solar disk, but still bright enough to be absolutely obvious, even to a casual observer. People stopped in the streets and simply looked up in a state of mild shock. This is really happening, they thought silently to themselves. A star exploded before our eyes, and now the sky has changed forever. The world became different overnight without warning. Astronomers around the world worked non-stop, analyzing the incredible streams of data from all the instruments. The spectra of the supernova showed the exact chemical composition of the ejected material in unprecedented detail. Each element of the periodic table left characteristic lines in the emission spectra. Oxygen dominated the visible part of the spectrum with bright green emission lines. Hydrogen created powerful red lines of the Balmer series across the entire range. Iron, silicon, calcium, and dozens of other elements appeared simultaneously in the infrared and ultraviolet regions. Detailed analysis showed that Betelgeuse created about 20 times the mass of our Sun in pure oxygen in its explosion. 3 solar masses of iron were synthesized in the fire of the core collapse, 1.5 masses of silicon, 1 mass of calcium, and significant amounts of all other elements. This oxygen will be enough for the atmospheres of thousands of Earth-sized planets in the future. This iron is enough for the cores of hundreds of new rocky worlds millions of years from now. There is enough carbon for organic life to arise on dozens of planetary systems one day. Betelgeuse created the building blocks of future worlds in its death. The atoms that are now expanding into space will become part of new stars in millions of years. Planets orbiting these stars. Maybe even life on the surface of some of these planets. The James Webb Space Telescope has captured the first detailed images of the expanding supernova remnant in the infrared range. The structure appears incredibly complex and beautiful in these high-resolution images. The gas cloud was not a simple spherical shell expanding uniformly in all directions. Instead, the images showed multiple layers of material moving at different speeds. Dense knots of gas were interspersed with sparse voids between them. Vortices and turbulent flows created intricate patterns in the cloud's structure. The asymmetry of the explosion was evident even in the earliest images of the remnant. One side of the expanding cloud was noticeably brighter and denser than the opposite side. The material moved unevenly in different directions from the center. The expansion speed varied from 15,000 kilometers per second in one direction to 25,000 kilometers per second in another direction at the same time. Why was the explosion so asymmetrical and uneven in structure? Theorists began to construct models to explain the observed features of the data. Perhaps the core of the star was rotating very quickly before the collapse, and this rotation affected the distribution of material. Perhaps magnetic fields inside the star directed the explosion predominantly in certain directions. Or perhaps there was a companion, a second star in a binary system that no one knew about before. On April 20th, a team of astronomers from Germany published an intriguing discovery in their observational data. They detected a faint additional source of X-ray radiation in the expanding cloud of the supernova remnant. The source was not located at the geometric center of the cloud, where the neutron star was rotating. It was offset to the side, closer to the edge of the visible structure of the nebula. The spectrum of this additional source indicated an extremely hot compact object with a surface temperature of hundreds of thousands of degrees. The team suggested that this could be a white dwarf, the remnant of a lower mass companion star. Betelgeuse may not have been a solitary star in space for its entire life. It may have had a companion in a binary system, orbiting around a common center of mass for millions of years. The companion was significantly smaller in mass and evolved faster than the red giant. It ended its life earlier, turning into a white dwarf long before Betelgeuse exploded. When Betelgeuse finally exploded, the shockwave hit this white dwarf with tremendous force. It heated its surface to incredible temperatures in a matter of hours. It tore off part of the material from the surface of the compact object and carried it away into the expanding cloud. The white dwarf survived this cataclysm, but was greatly altered by the impact of the explosion. The interaction of the shockwave with its companion elegantly explained the observed asymmetry of the supernova remnant. The wave reflected off the dense object and created secondary shock fronts in the material. These multiple waves interfered with each other in a complex way. They created the observed uneven distribution of gas density in different directions of space. The story of Betelgeuse became richer and more complex with each new discovery by scientists. It was not a lonely star, heroically dying in the isolation of cosmic emptiness. A binary system where one partner had long since died and turned into a dead remnant. The second partner followed the first into death a century or millennium later. The white dwarf remained the only living witness to the catastrophe, surviving the explosion of its massive companion. May 2026 brought a slow but noticeable decrease in the brightness of the supernova in the sky. The peak luminosity lasted for about 3 weeks after reaching its maximum brightness. Then the brightness began to fall steadily day after day without stopping. Not quickly and dramatically, but slowly and gradually. A month after the explosion, the supernova was about half as bright as its peak brightness, according to measurements. 2 months later, the brightness had fallen 4 times from its maximum. The brightness curve, a graph showing how brightness changes over time, closely matched the predictions of theoretical models of massive star explosions. There was a sharp increase in luminosity a few hours before the peak brightness. This was followed by a plateau of maximum brightness lasting several weeks. Then, an exponential decrease in brightness over time, continuing for months and years after the explosion. The energy source powering the supernova's glow slowly depleted with each day of observation. In the first weeks after the explosion, the cloud glowed mainly due to the enormous thermal energy accumulated at the moment of the shockwave. The gas was heated to billions of degrees and slowly cooled, emitting light outward. Then, the main source of energy became the radioactive decay of unstable isotopes created in the explosion. Nickel-56 decayed into cobalt-56 with a half-life of 6 days. Cobalt-56 then decayed into stable iron-56 with a half-life of 77 days. Each decay released energy in the form of gamma rays, which heated the surrounding gas from within. In July 2026, 3 months after the explosion, the brightness of the supernova had fallen to about the brightness of the full moon, still incredibly bright by astronomical standards, bright enough to cast faint shadows from objects on the ground at night, bright enough to be visible even in daylight as a dim red dot, but no longer dominating the entire sky as overwhelmingly as in the first weeks. People gradually began to get used to the changed sky with each passing day of normalization. Life slowly but surely returned to its normal rhythm of work and everyday life. Offices were once again filled with employees, and schools resumed classes after the chaos of the first few weeks. The economy recovered from the temporary shock of the cosmic event. The world continued to turn and exist, despite the dramatic changes in the sky. But something fundamental had changed in the collective consciousness of humanity forever after that night. People now looked at the stars differently, with a new understanding of the reality of space. The stars were no longer eternal, unchanging points of light in the celestial sphere. They were dynamic objects, born and dying in the cosmic dance of matter and energy, alive in some deep sense of the word. Every star in the night sky will die someday, just as Betelgeuse died. Some will explode in supernovas millions of years in the future. Others will quietly fade away, turning into white dwarfs after billions of years of evolution. But all of them are temporary. All of them are finite in their existence. Only the time scales differ enormously between them. September 2026, 5 months after the explosion, the brightness has decreased to approximately the second magnitude on the astronomical scale. It was still one of the brightest points in the planet's night sky, but it was no longer dominant, no longer overwhelming everything else with its light. The constellation Orion slowly returned to its recognizable shape for observers. The hunter's shoulder was again marked by a bright star, although it was significantly brighter than Betelgeuse had been in its normal state as a red giant. Detailed chemical analysis of the supernova remnant continued methodically month after month of observation. A team from the California Institute of Technology published a comprehensive catalog of all the elements detected in the spectra. Thousands of hours of observation time were spent on this work systematically. Millions of individual spectral lines were identified and measured with the highest precision. The results revealed the chemical composition of the ejecta in incredible detail, unattainable for any previous supernova in the history of astronomy. The explosion produced the building blocks for thousands of future planetary systems in the galaxy. There is enough oxygen for the atmospheres of countless worlds over millions of years of evolution. There is enough carbon for the basis of organic life on dozens of systems one day. There is enough iron for the metallic cores of hundreds of rocky planets in the distant future. All the heavy elements necessary for complex chemistry and life were present in abundance in the expanding cloud. Betelgeuse died, but its death was an act of cosmic creation at the same time. The seed of the future, planted in the death of the present to blossom through eons of time. The gas cloud will expand for thousands of years, gradually mixing with the interstellar medium around it. In millions of years, it will become indistinguishable from the surrounding gas of the galaxy. The atoms will scatter across a vast volume of space. They will become part of a new molecular cloud somewhere in the spiral arm of the Milky Way. The cloud will slowly collapse under its own gravity. New stars will be born from this material. Planets will form around the young stars. Perhaps life will one day arise on the surface of some of these worlds. Oxygen atoms from Betelgeuse will become part of the atmosphere of a distant planet tens of millions of years from now. Carbon atoms will become part of organic molecules that will one day become living organisms. Iron atoms will form the metallic core of a new rocky world, creating a protective magnetic field around the planet. We are all made of stardust, and this phrase was no longer an abstract metaphor. Humanity saw with its own eyes how this dust is created in cosmic furnaces. We witnessed the birth of elements that will one day give rise to new life somewhere in the universe. We witnessed the fundamental process of cosmic evolution of matter from simple to complex. December 2026, 8 months after the explosion, the brightness dropped to about magnitude +2 on the astronomer's scale. It was still visible to the naked eye as a dim reddish star in Orion's shoulder, but it was no longer impressive or attracting the attention of casual observers. Most people had returned to their normal lives, completely forgetting about the drama in the sky. Only astronomers and enthusiasts continued to closely monitor the evolution of the remnant methodically. The nebula continued to expand at speeds of tens of thousands of kilometers per second. Its visible size in the sky slowly grew month after month of observation. By the end of the year, the remnant occupied an area about half the angular size of the full moon. It was too faintly distributed over this area to be visible to the naked eye, but it was stunningly beautiful in large telescopes with long exposures of photodetectors. Detailed, high-resolution images revealed the incredible complexity of the nebula's internal structure. Filaments of dense gas were intertwined in intricate patterns throughout the cloud. Knots of increased density glowed brighter than the surrounding sparse areas. Voids and cavities pierced the structure unevenly in various places. Turbulent vortices created spiral patterns in the streams of expanding gas with grace. Each chemical element occupied its preferred region in the nebula's space. Oxygen was concentrated mainly in certain layers of the cloud, glowing with a characteristic green color in special instrument filters. Hydrogen dominated in other regions, creating a rich red emission glow. Sulfur, nitrogen, and other elements manifested themselves independently in their specific areas of the structure. Composite color images combining data from different filters created truly breathtaking pictures of cosmic beauty. The rainbow of colors showed the chemical composition of the emission in a visually understandable way. Art and science merged together in these images of the majestic death of a star. Astrophotographers around the world patiently created stunning images of the nebula. The remnant of Betelgeuse became one of the most photographed objects in the planet's night sky. At the geometric center of the expanding cloud, a neutron star spun, the last remnant of what was once a majestic giant. It was about the size of an average city on Earth, but its mass exceeded that of the Sun. The density of the matter is so incredible that a teaspoon of neutron star material would weigh 1 billion tons on Earth's scales. Gravity on the surface is billions of times stronger than Earth's gravity. The magnetic field is 1 trillion times stronger than the most powerful magnets ever created by humankind. The neutron star rotated around its axis incredibly fast, 33 revolutions every second. Each revolution created a pulse of radiation that pierced space with a narrow beam of light and radio waves. A pulsar was born in the heart of Betelgeuse, a cosmic beacon that will shine for millennia into the future. Radio telescopes around the world detected the pulsations almost immediately after the star exploded. Regular pulses with a period of exactly 33 milliseconds came methodically from the center of the nebula. They were as stable as the most accurate atomic clocks. But astronomers knew that this stability was temporary by cosmic standards. A neutron star slowly loses its rotational energy through radiation. The period will gradually increase year after year. In thousands of years, the pulsar will slow down so much that it will no longer be visible in the radio range at all. It will turn into an ordinary cold neutron star without radiation pulsations. But that is in the distant future of civilization. Now, the pulsar is alive and active, emitting powerful streams of energy into the surrounding space. A relativistic particle wind blows from the rotating neutron star in all directions simultaneously. Electrons and positrons, accelerated to speeds close to the speed of light, collide with the expanding gas of the nebula. They heat it up further. They create complex structures of interaction between the wind and the matter of the cloud. In February 2027, 10 months after the explosion, the scientific community held a large-scale international conference. The Betelgeuse Supernova Science Summit brought together thousands of researchers from around the world. They exchanged data, discussed results, and planned future observation campaigns for years to come. The director of NASA gave a solemn speech to the audience of assembled scientists. "A year ago, we witnessed the death of a star," he said excitedly. "An event that statistically occurs in our galaxy several times a century. But the last supernova visible to the naked eye was observed in 1604, Kepler's supernova, 423 years ago. Generations of astronomers dreamed of seeing such an event in their lifetime. We were the lucky ones who saw it with our own eyes. The data collected during this year of intensive observation will change astronomy for decades to come. We have learned more about the physics of massive star explosions, than in the previous century of theoretical research combined. We observed the processes of nucleosynthesis of heavy elements in real time. We saw the birth of a neutron star from a collapsing core with our instruments. We recorded the expansion of the remnant with unprecedented detail. We witnessed the greatest cosmic event in modern human history. Applause rang out long and sincerely from the audience. Scientists understood deeply that they were living in an exceptionally privileged time in history, a time when space showed its true face through drama and beauty, a time when the sky was transformed before the eyes of a single generation. May 2027 brought an interesting scientific discovery in the data from these long-term observations. An amateur astronomer who patiently tracked the brightness of the remnant every clear night methodically noticed small periodic fluctuations in the luminosity of the nebula. The brightness did not decline in a completely monotonous and smooth manner, as expected from simple models. There were small variations up and down relative to the average brightness curve. The period of fluctuations was approximately 3 to 4 weeks between successive intensity maxima. Other observers independently confirmed the detection of these variations in their data. The fluctuations were real, not instrumental artifacts of the measurements. What could cause such periodic variability in the brightness of the supernova remnant? One team of theorists proposed an explanation involving the radioactive decay of unstable isotopes. Different radioactive elements decay with different characteristic half-lives. The superposition of several exponential decay curves can create a complex pattern of luminosity variations over time. Beats between different half-lives can manifest as the quasi-periodic brightness fluctuations observed. Another group proposed an alternative explanation through the activity of the central pulsar. The neutron star emits unevenly for various reasons related to its internal physics. Periodic bursts of pulsar activity heat the surrounding gas with pulses of energy. They create temporary increases in the overall luminosity of the nebula observed from the outside. A third hypothesis linked the fluctuations to the dynamics of the expansion of the cloud of material itself. Dense clumps of gas move at different speeds in a turbulent flow. Faster clumps periodically catch up with slower areas ahead. Collisions between clumps release the kinetic energy of motion. They heat the gas at the points of contact. They create temporary bright areas in the structure of the nebula. No one knew the exact answer to the question of the causes with absolute certainty, but the fluctuations added another layer of complexity to understanding the evolution of supernova remnants. Another reason to continue careful, long-term observations of the system methodically. In September 2027, a year and a half after the explosion, the nebula reached a visible size approximately equal to the full disk of the moon in the sky. The integrated brightness was distributed unevenly over this large area. The surface brightness dropped so low that the remnant became virtually invisible to the naked eye. Only with sufficiently powerful amateur telescopes could one discern a faint, misty glow at the site of the former star. For most ordinary people, Betelgeuse had completely disappeared from the night sky for good. The constellation Orion now looked incomplete and mutilated to observers. One shoulder of the hunter was empty and deprived of its bright star forever. The sky had changed irreversibly during the lifetime of an entire generation of people for the first time in millennia. But the astronomy community kept working on studying the remnant systematically. Articles were published weekly in scientific journals around the world. Conferences were organized regularly to share results between groups. Data was openly shared through international databases. Models of massive star evolution were constantly revised to account for new observations. The understanding of the physics of supernova explosions advanced decades during these months of observation. Theories were refined relentlessly under the pressure of real data. Predictions for other red supergiants were adjusted accordingly. Antares in the constellation Scorpio, Mu Cephei in the northern hemisphere, other massive stars, all of them were now being observed much more closely than before. Astronomers were methodically searching everywhere for early signs of impending instability. Who would be the next to explode in the foreseeable future of humanity? In January 2028, almost 2 years after the event, NASA announced plans for an ambitious interstellar mission to the remnant. The project was named Betelgeuse Explorer, an automatic probe to study the nebula from within. The mission's objectives included flying directly through the expanding gas cloud, collecting samples of material for detailed analysis of its composition on site, measuring the density, temperature, and velocity of the substance in situ, approaching as close as possible to the central pulsar to study the neutron star in detail. Of course, the practical problems of such a mission were incredibly difficult to solve. 600 light-years of distance, even at relativistic speeds, would require at least thousands of years of travel. Modern propulsion technologies are completely incapable of providing sufficient speed for the probe, but engineers were optimistic about the future development of thermonuclear engines, or photon sails, accelerated by powerful lasers from Earth's orbit. Travel time could one day be reduced to centuries instead of millennia. The launch was tentatively planned for the year 2042. By the time of launch, the technology may have advanced far enough for practical implementation. The probe will reach the vicinity of Betelgeuse sometime between 742 and 942 in the most optimistic scenarios. A distant future that only our distant descendants hundreds of generations from now will see. But the act of planning and sending such a mission had a deep symbolic meaning in itself. It was a message to ourselves and the universe about humanity's intentions. We are not just passive observers of cosmic events around us. We are active explorers, striving to understand and touch what we see with our eyes. We will not stop at the barriers of distance and time in our curiosity, even if the results will only be seen by our distant descendants after thousands of years of evolution. March 2028 brought a philosophical essay from a well-known contemporary thinker. The title of the work is Betelgeuse and a New Understanding of the Mortality of Human Existence. The topic is broad: how observing the death of a star changed the collective perception of the finiteness of life. The author wrote deeply and soulfully about the fundamental questions of existence. For millennia, people have looked at the stars as eternal objects in the universe, constant, unchanging, divine in their geometric perfection. The gods placed them in the celestial sphere at the beginning of time. They remained motionless for generation after generation of observers. Our ancestors saw the same constellations thousands of years ago. Yes, science explained the life cycles of stars theoretically long ago. Astronomers knew that stars are born and die according to the laws of physics, but knowledge remains abstract without direct empirical confirmation. Seeing is concrete, real, impossible to ignore or easily forget. We saw death with our own eyes in real time, not a distant galaxy, invisible without powerful telescopes, not an archival supernova that happened centuries ago before the invention of photography. A star that our ancestors saw regularly for thousands of years, which we ourselves had seen all our lives until that moment, which was a part of the sky, culture, and mythology of civilization. Betelgeuse died before our eyes in one night, forever. And in its death, we saw a clear reflection of our own inevitable fate. We are absolutely temporary. Everything around us is temporary by nature. Even the stars, giants that have shone steadily for millions of years, even they will fade away forever and irrevocably someday. But Betelgeuse's death also revealed another profound truth about existence. Death is not meaningless on a cosmic scale. It is not the end without a continuation of the history of matter. The star died physically, but created chemical elements in the process. It died as an object, but gave birth to a neutron star at its center. It died as a source of light, but left a nebula as the seed of the future. A nebula that will one day, millions of years from now, become part of new star systems, new planets orbiting young stars, perhaps new life on the surface of some worlds of evolution. Death is the transformation of matter, not its destruction. Energy is conserved according to the fundamental laws of physics. Matter does not disappear into thin air without a trace. The form of its configuration changes dramatically, but the essence of atoms remains eternal and unchanging forever. And we are an inseparable part of this eternal cycle of transformation. The atoms in our bodies were born in the cores of ancient stars billions of years ago. They died in the fire of supernovae long before the birth of the solar system. They slowly scattered across the galaxy in clouds of gas. They gradually gathered in the protosolar nebula through gravity. They became the planet Earth through the accretion of matter. They became life through the evolution of complexity. They became us through billions of years of continuous transformation. We will inevitably die physically someday according to the laws of biology. Our bodies will decompose organically in the soil of the planet. Atoms will gradually disperse into the environment, but they will not disappear into nothingness completely. They will become part of the soil that nourishes the plants around them. Plants will become food for other organisms in the biosphere. The cycle will continue indefinitely as long as life exists on Earth. We are immortal at the atomic level of matter. We are temporary only at the level of the current configuration of atoms, and this is normal, natural, and beautiful in its inevitability. Because the value of existence is not in the eternity of configuration. The value is in the moment of awareness, in the experience of reality. Betelgeuse existed for millions of years as a stable star without interruption. But its greatest moment of significance came at the very end of its life, in death, when it created elements for the future, when it lit up the sky with the incredible light of drama, when it inspired an entire civilization to look up in awe. Our lives are objectively much shorter than the stellar timescales, decades versus millions of years of a star's existence. But our moments are no less valuable to us subjectively. Every moment of conscious existence is an incredible miracle. Every connection with other living beings is an irreplaceable treasure. Every glance at the stars at night is a touch of eternity within reach. The essay ended with a call to cherish every moment of existence. Betelgeuse reminded us of the fragility and beauty of life at the same time. Everything is temporary, but that is precisely why everything is incredibly precious. Live fully, love deeply, look at the stars often. Because we are all temporary configurations of eternal atoms, we are fortunate to be aware of our own brief existence. The work instantly became a bestseller of philosophical literature around the world. People read it, cried, and deeply rethought their priorities in life. The supernova gave not only scientific data to professional astronomers, it gave a philosophy of meaning to all of humanity at large, a cosmic perspective on ordinary earthly life, the context of eternity for understanding the temporary existence of each individual. The years passed slowly but steadily with the flow of time. The nebula continued to expand, fade, and evolve in a structurally complex way. The pulsar at its center continued to rotate, slow down, and emit energy methodically. Astronomers continued their observations, publications, and conferences regularly. Life on Earth continued to flow at its established rhythm, inexorably. Children born at the moment of the explosion, April 15, 2026, grew up gradually under a changed sky. They did not personally remember that bright night of the first light. They were too young at the time of the historic event. But their parents told them stories over and over again. They showed them photographs and videos that had been preserved. They patiently explained the significance of what had happened. These children will grow up with a unique and profound understanding of space. They will know intuitively that the sky is not static and unchanging forever. Stars are born and die in the cosmic dance of matter. The universe is dynamic, alive, constantly transforming around us. They are the Betelgeuse generation, marked by space in a special way. Witnesses to the greatest event, though too young for direct memories. Many of them will choose careers in the science of the future with inspiration. Astronomy, physics, and space systems engineering will be actively pursued. Betelgeuse has inspired a whole generation of young sky explorers. The future of humanity was shaped invisibly by the light of a dead star. Decades will inevitably pass before humanity. The nebula will gradually expand to dozens of times its current size. In a century, it will occupy several degrees of the sky. Its integrated brightness will be distributed thinly over a huge area. Its surface brightness will fall below the visibility threshold of most instruments. In 1,000 years, the remnant will become visually indistinguishable from the interstellar medium. Only specialized radio and X-ray telescopes will be able to see its structure faintly. The pulsar will continue to rotate and emit radiation for millennia, but slowly, steadily slowing down as it constantly loses energy. In 1,000,000 years, Betelgeuse's atoms will be completely scattered throughout the vast volume of the galaxy. They will mix indistinguishably with the surrounding gas. They will become part of a new molecular cloud somewhere in a spiral arm. The cloud will slowly collapse under gravity. New stars will be born from the recycled material. Planets will form naturally around the stars. Perhaps life will evolve on some of these worlds, and that distant future life will literally contain atoms from Betelgeuse. The oxygen in their atmospheres will be partly produced by our supernova. The carbon in their organic matter will be partly created in our explosion. They are distant descendants of Betelgeuse genetically through chemistry. Children of a dead star, completely unaware of their origins. The cycle of cosmic evolution continues forever without stopping. Stars are born slowly from gas by gravity. They live for millions or billions of years in stability. They die in fire or quietly, depending on their mass. They generously return enriched material to the interstellar medium. New stars are formed from enriched gas again. The cycle repeats endlessly as long as the universe physically exists. We are temporary witnesses to one brief moment of this eternal process. We are observers of Betelgeuse's death specifically. But through understanding this event, we touch eternity deeply. We see how the cosmos works fundamentally. We understand our place in the great chain of being clearly. Look closely at Orion tonight, if the sky is clear above you. Find the distinctive belt of 3 bright stars in the center. Look closely at the hunter's shoulders above the belt. The right shoulder is marked by the bright blue star Bellatrix, as usual. The left shoulder is empty where Betelgeuse once shone brightly. The void is not quite absolute, however. There, a nebula of remnants expands, invisible to the naked eye. It is a cloud of atoms traveling through space at incredible speeds. It is the seed of future worlds, patiently planted in the death of the past. And in the center of the cloud, a pulsar spins tirelessly. A neutron star, a monument to what was once a great giant. A cosmic beacon that will easily outlive our civilization. Perhaps it will outlive humanity itself as a species. The constellation looks wrong and crippled now, forever. The hunter has lost one shoulder in a cosmic battle, irreversibly. The sky has changed in the lifetime of a single generation for the first time in millennia, and this change will remain visible for centuries to come at least. But there is a profound philosophical beauty in this change, a reminder that nothing is absolutely eternal. Everything flows, everything transforms, everything changes inexorably. Even the stars, even the constellations, even the cosmos itself evolves. The only constant in the universe is continuous change. The only eternity is the endless transformation of matter and energy. Betelgeuse has physically disappeared from view forever, but it remains everywhere, metaphorically and literally. In the atoms of our bodies, created by ancient supernovae. In the data of our computers, storing scientific information. In the memories of our minds about that incredible night. In our children's dreams of stars and space exploration. It gave us a priceless gift in its death, not just a beautiful sight for admiring eyes, a profound lesson about the nature of existence, universal, a lesson about life, death, transformation, the eternity of moments. We were there under that red light, witnesses. We saw with our own eyes birth and death at the same time. We understood more deeply our place in the cosmos forever, and this understanding changed us irreversibly as a species. We can no longer look at the stars naively and thoughtlessly. We now know that every point of light has a dramatic history. Every star lives, evolves, and dies according to the laws of physics, and we are literally the products of these lives and deaths. Children of the stars, looking at their parents with a new understanding. The memory of Betelgeuse will live on as long as intelligent humanity lives, as long as someone looks at Orion thoughtfully on winter evenings, as long as someone remembers the nights when the sky glowed with red fire, as long as someone carefully passes on stories to future generations. We were there at that moment in cosmic history. We saw the grandeur of the universe firsthand. We touched eternity through a temporary event, paradoxically, and it changed us forever, deeply and irrevocably. We are the Betelgeuse generation now and forever, marked by space, inspired by a star, changed by the light of a dying star. Its legacy will live in us and through us forever.